This is the lecture 5 of this video series, and today we are going to talk about unions in C++. In C++, unions are similar to a structure and the classes. Like a structure, union is also a user-defined data type. That means when you create a union, you can group the elements of different data types together, and the name of that union becomes a new user data type. In C++, unions may contain both member functions and variables. So if you are from the C programming background, then you must be knowing that when you create a union, you can just create the member functions within that union. But in C++, you can create the member functions as well as data members within the unions. Unions may also include the constructor and destructor functions similar to the classes. So when you create a class, you can create the constructor and destructor functions. So what are they? They are used to initialize the members of that particular class or that union. So in C++, it is also possible to include the constructor and destructor functions for the unions. We'll talk about constructor and destructor in upcoming videos. Like structure, union members are by default public. So as we saw in the previous lecture, when you create a structure, all the members present within the structure are by default public, so they can be accessed outside that structure. But in case of classes, all the members are by default private, so they cannot be accessed outside the class, and they can be accessed only through a public or protected members of that class. But in case of unions, all the members are by default public and they can be accessed outside the union by using the union variable. The last point, and very important, unions in C++ retain all of its C-like features, and the most important being that all the data elements share the same location in memory. If you create the different elements or different data members in the union, all they share the same memory location. We'll see this point by some examples. So let's write some code to understand the unions. First, I'll create one entry function. It is a main. Then I will include this IO string header file to support the input output operation, and then this using namespace std statement to resolve the scene and cout objects. Now we'll create a union. To create a union, you have to specify this union. This is a standard C++ keyword, and what follows after this keyword is the name of union. I'll create a name of union as a temp underscore key, and then these two curly brackets ending with the semicolon. The syntax is similar to a structure or a class. Inside this union, we can specify the different data members or member functions. We'll create some data members. First one is a integer data one, which can hold the integer values, and then character data 2, and this is array of character, which can hold the max 4 characters. By default, all these data members are public, so they can be accessed outside the union. You can also specify the access specifiers. So when you do this, when you say the private access specifier, now these members are private to this union and they cannot be accessed outside the union. Similarly, you can create a public access specifier. Now inside this, I will write one member function that will display the contents of this union members onto the console window. So for that, I will use this cout object and then this insertion operator and the variable of union. Now this /n is a new line, so this variable, the next statement after this insertion operator will be printed on the new line. So in short, the new line is inserted after this data1 variable. So we saw how to create a union, how to create the member variables and member functions within the union. Now we'll create a variable of that union. To create a variable of union, you have to specify the name of union, in this case temp underscore t, and the name of that union variable, say t1. Now with this variable, we can access the elements of union. To do that, you have to specify the t1. There is a name of variable, dot operator, and the name of that member function or member variable. Now in this case, you can see when I specify this dot operator, I can see only this display data function. Since this is a data2 and data2 are private, they are not accessible by this d1 variable. So you can access only this display data function. And then I will write this while one statement here so that my program doesn't exit. Alright, so let's compile the program and see what does it outputs. But one more point we forgot. Here we have not initialized this set variables, and if you don't do, it will print some garbage value or some zero value. So as we saw in the case of structures, we can do this in-place initialization. That means when you create a structure variable, in the same line we can initialize all the members of that structure. So in case of union, it is not possible. So you cannot do in-place initialization in case of union. So we have to initialize them from somewhere else. So we'll initialize these variables here. First one is a data variable, data1. I will write some value here, say 30, and then this data2 variable. So this is a character. I will write some characters. So we initialize all the members of this union, and we are printing them on this line. Now let's compile the program and let's run it to see what does it outputs. Now to your surprise, it has printed the value of data1 as something 1684 or some value, and then this ABCD 4 characters. So this looks correct, ABCD looks correct, but this doesn't seem to be a correct value, because here we specify this data1 as a 30 and it's printing something else. Why it is so? And this is because, as we talked before, all the members within the union shares the same memory location. That means this data1 is also pointing to the same memory location, data2 is also pointing to the same memory location, and whatever we are writing all is going into the same memory location. What we did here, we first wrote data1 as a 30. So suppose memory location 1000 to 1004 are allocated for this data1 variable, which is of 4 bytes. Then first 30 will be written into those 4 memory locations. Then immediately you are writing this another variable data2, which is also getting stored into same memory location. And when we do this, the first content 30 is overwrite by this second content, that is this for data2 variable content. So that's the reason we are seeing output as data1 has some garbage value, and no, it's not a garbage value for information. So this is a equivalent of this ABCD 4 characters. That value is the equivalent of this 4 characters. So I hope now you have understood what is the meaning of this shared memory location and how it is happened in case of the union. Alright. So why do we need this union at the first place? Where we can use this union? The common examples of these unions are when you want to swap the variables, content of variables, or we want to change the endianness of your variables. Then unions are very useful. We'll understand the unions by taking one example of changing the endianness of your variable. So first I will delete this program. So create another variable, another union, and I will call this as endianness. What is endianness? When the microprocessor designing was happened, the different vendors created their own architecture, and in some cases of and this architecture has effect on storage of the variables into a memory. Now in case of some processors, the variable is stored in different manner, and in case of some other processors, the variable is stored into some different manner. Let's see how this variable can be stored into a memory location. So I'll give one short example here. Let's assume you have some memory locations, and these addresses are starting from this 0x1000. So we have one memory block, and these four memory locations are present. And inside this memory locations, we'll store some variable. Let's assume this is our data. Data is a 1, 2, 3, 4, 5, 6, 7, 8. Data is a 4-byte data. How 4 byte? This is 1 byte, this is 2, this is 3, and this is 4. So this is a 4-byte or 32 bits data. To store this 4-byte data, we need 4 memory locations. So that's why I wrote this 4 memory locations. Now, how this data will be stored into these memory locations? This data, as per the or depending on the microprocessor architecture, will be stored into two different manners. Let's see how. First, it can be stored like this. And then this data can also be stored like this. So this data can be stored in by it's possible to store this data in these two different ways depending on the architecture. So what is happening here? Here this is first byte of the data, and this is a most significant byte. So this is the first, it is called as the most significant byte. So I'll write here MSB, that is the most significant byte, and this is LSB, which stands for the least significant byte. So here 12 is the most significant byte and 78 is the least significant byte. This manner of the data storage, first the MSB is stored into this lowest location of memory, that is 1000, and then this 3, 4, 5, 6, and finally 78, which is the least significant byte, is stored onto the highest address of this memory location, or the 4 bytes of this memory location. In this another manner, the least significant byte is stored into this lowest address of this memory location, and the most significant byte is stored at the highest address of this memory location, that is 1002. So when microprocessor does this, the scheme is called as a big endian, and this is called as a little endian. Remember, this is not Indian, this is Indian. So this, okay. So we saw there are two ways this data can be stored, one in the big endian and another in the little endian. So in big endian, first this most significant byte is stored at the lowest address, and then the least significant byte is stored at the highest address. To remember it clearly, you can say in the big endians the data is stored as it is. You can see data is stored as it is, when in little endian it's actually swapped. So 78 came here and 12 came here. Alright. So we saw how this endianness work. We'll write a program to change the endianness of program. And why do we need that? Suppose we have one processor which is using the big endian scheme, and now we want to port your program onto the another processor which uses a little endian scheme. Then in that case, all the variables you should first convert into the little endian format, and that's where you need this function which converts your variables into a, or which changes the endianness of your variable. Another example is if you're working in the embedded system programming, then it might be possible you will be working on the TCP/IP or UDP, that is a networking, and in some cases your the, the processor and that protocol endianness is different. Then in that case, you might want to convert the variable endianness before sending the data over the network layer. We'll write code that will convert the Indianness for the up to a 64-bit number. So that is a 8 byte number. For that, I will first create one variable. So this is unsigned long data. So why I have created this long, because this, when I say this long data type unsigned long, this data one is becomes a 64-bit wide or 8 byte wide. Now this depends on your target processor. Since my target processor is Intel i5, for which I am developing writing this program, so my this unsigned long type for this Microsoft Visual compiler will be considered as a 64-bit or 8 byte. I will create another variable, and this is of unsigned character. I will name this as a data2, and this I will make as a 64-bit or 64 characters wide. Now as we saw earlier, this data1 and data2 members in the union shares the same memory location. So content of this data1 variable and the data2 variable will be same all the time. So with this important feature of union, we will see how we can change the Indianness of the variables. By default, all these members are a public. So let's write the access specifier to make them as private. And I will write another member function inside this public access specifier that will change my Indianness. Here I will create the variable of this union, say d, and I will create another variable here, say unsigned long or unsigned integer as temp. Inside this variable I will store one value. So now this unsigned integer is a 4 byte wide or 632 bits wide. So I can store the max 32 bits of data into this. We will change the Indianness of this data temp. For that, I will call this function. So how I can call this change Indianness function is by using this t, that is the name of the union, and then this function name. And inside this, I will pass this variable which I want to change the Indianness. But I will not pass the variable here, I will pass the address of variable. Now this is called as a call by reference. When you pass the parameters to a function, there are two ways to pass, one by the call by value and call by reference. When you use the call by reference, we are actually passing the address of that variable, and in case of call by value, we are actually passing the value. So why I need to pass the address is because I want to change this variable in this function itself. So that's why I need to pass the address of that variable. The second parameter is I will pass is the size of this variable. Why? Because I need to know for how big my data is, and knowing that it is required to know that, because with that size I can change the Indianness. Here I also need these two variables which I'm passing here. First thing is we are passing this address of this variable. Now here we can, since this temp one is an unsigned integer type, we can create a pointer variable of the unsigned integer type, say ptemp. But the problem is we are not only passing the variable of unsigned integer type. If you want to change the Indianness of variable which is of unsigned long integer, that is 64-bit wide, then your data type will be different. Then if you are passing the same data type here, which is unsigned integer, then it won't work, because this is a 32-bit wide, while unsigned long integer is of 64-bit wide. So you must specify some generic data type here, and that is possible by specifying this void pointer. So what is this void pointer? Void pointer is a generic data type, or it is a generic pointer. That means if you pass the variable of any particular data type, then this pointer becomes uh, then this pointer becomes of that particular data type. So if you're passing the variable of unsigned int, then this ptemp is of unsigned int type. If you are passing the variable of unsigned long int, then this ptemp will become a of unsigned long int type. So that's why we need this generic data type, generic pointer void. The second parameter we need is a size. So now this size is going to be very short, and that can be fitted into this unsigned character data type, which can holds max 255 value. So I'll specify this as a size. First thing what I want to write here is some if case, and why if case is because the size will change. So as per the my data variable and data type of that variable, the size will change. It will be 4, it will be 8, or it can be a 2 based on the data type. So I have to check for which size I am performing the Indianness operation, because each operation will vary based on the size. So I will check here if size equal to, then here I will write the size of unsigned integer. So this inside this if statement or if case, I will write a code that will convert the Indianness, change the Indianness for the variable of this unsigned int type. Similarly, I can write a if case for the another data type of say unsigned long integer. Similarly, I can write for another data type say unsigned short. Unsigned short is another data type, and it can hold the max for 2 bytes at a time. So unsigned short data type is always of a 2 bytes wide. First, we'll write a program for converting this variable of unsigned int type, or we'll write a program to change the Indianness of this unsigned int variable. Let's first create one variable of unsigned int, and I will call this as a temp. And inside this temp, I will store the value of this ptemp variable. So what this ptemp is holding is actually holding the address of this temp variable. And if I want the value of that variable stored into that address, I have to use the star and then the variable name, so asterisk and the variable name, which indicates the value of that variable. This we saw in the previous lecture of structure, where we wrote a program to access the elements using the pointer, structure pointer. So I will write this ptemp. Remember, you cannot just write the asterisk here. Why? Because this void is a generic pointer, and when we are taking a value or extracting a value from this variable, you must typecast it with the proper data type which you are here storing. Now in this case, we are considering the ptemp as unsigned int, as we are passing the unsigned int value to this, and whenever we are extracting the value, which is also called as a dereferencing the pointer, we must specify the correct data type. So that is unsigned int and this asterisk operator, and then this star sign before that typecasting. Now this temp will uh, hold the value of this ptemp variable, or actually the value of this value present in this address. Alright. Now how I can change the Indianness? So Indianness is nothing but changing the bytes of this variable, or swiping the bytes of this variable. So what I have to do is, first thing, this 78 must be moved here, then 56 must be moved here, then the 34 must be moved here, and finally this 12 must be moved here. So then that will change my Indianness. So how we can do this? First I will write a program for that, and then we'll see how it will work. Alright, so I wrote here one statement is actually a for loop. and this for loop will iterate for max size minus 1 times, actually the size times. So what is size here? The size depends on the type of data. So suppose we are passing the unsigned int as the size of unsigned int, that is a, which is a 4, then this loop will iterate for the 4 times. How? The size minus 1, which is a 3, and we're checking for the condition I greater than or equal to 0. So from 0 to 3, that is a 4. So this loop will iterate for the 4 times. Now inside this loop, first I wrote one statement. So, but before that, what I did, I have created this variable of this union. So Indianness is a union, and I created this variable utemp. I'm initializing this data1 variable as 0 inside this. Then here, another variable is of a character type, which is array of character. So what I'm doing is first, for this index I, data2 of I, I'm ORing the content of this temp, and I'm this typecasting this temp to an unsigned character. So that means if temp is suppose is a 0x1234, then when I'm typecasting with unsigned character, it will just take this last 2 bytes, that is 34. So assume our past data is this 124556768. So when I do that, the first thing it will take 78, and it will OR with this data2 of I, so which is an array of character, and where I is pointing, it is pointing to a size minus 1, so size is a 4, assume, then the I will be 3, so it is pointing at the highest index, that is the third index. Then we are shifting this temp by a size of 8 or 8 bits. So what will happen if temp contains this value, then if you shift by 8, it will actually shift this, it will actually remove this, 78, and it will be stored like this. So now the new value will become a 00123456. Alright. So since we are iterating this loop 4 times, in the next loop what will happen, now this temp will contain this value next time. So 70 is gone, and the least significant byte is now 56. So we'll OR this, or this OR is not required, we can just specify equal, and then the data of I, then I next time is becomes 2. So since we are decrementing here, the data2 of 2 will be storing this 56. Then we'll again shift this temp by the 8 bytes, right shifting to 8. So next time it will become a this 00001234. So we'll iterate this loop one more time, and we'll get the least significant byte of 10, which is 34. And again the next time we'll shift this 10 by 8. So finally it will become a 0x12. So this will do one more time, so that all my data will come in this character array in the shifted form. So my most significant byte has come to LSB position, and LSB position has come to a MSB position. So this is how this Indianness changing is happening. So after this, now as we have seen here, this data2 and the data1 variable shares the same memory location. So we'll take the advantage of this property, and what we'll do is, now what is happening here is the content of the data2, which is actually swapped content, is already moved into this data1 variable. So we will copy the content of this data1 variable directly into this ptemp variable. So what has happened now, when I do this, again it is dereferencing. Since it is a generic type, we have to specify some proper data type here. And then this asterisk sign, which indicates the value. So what we are doing, we are copying the content of this data1 variable, which is now swap content or Indianness change content, into this content of this ptemp variable, which is nothing but storing the address, and we are actually storing that data into this address, memory address. So what we achieved here is we completely changed the Indianness of this temp variable using this piece of code. Now let's write this cout statement here to print the value of this variable before changing the Indianness and after changing the Indianness. So I print it on the next line. First, let's compile the program and see whether it is giving any error or not. Compiled successfully, let's run it. Now it is printing in terms of a decimal, so we'll print it in terms of hex so that we'll better understand what it is printing. To print into the hex value, you have to specify this hex and then insertion operator. Similarly here hex and then the insertion operator. Now you can see my original data is 1 2 3 4 5 6 7 8, and after this change in Indianness, now it has become 7 8 5 6 3 4 1 2. That's great. So we wanted the same output. The 7 8 has moved to this MSB position and 1 2 has moved to this LSB position. Similarly, this 5 6 came here and 3 4 came here. Alright, so our program is working. Now we'll see how we can change the Indianness for this unsigned long integer variable. For that, we have to just copy this code, paste it here, and now change the data type of this variable unsigned long int. Similarly here as well. The rest of the code will remain same, and here you have to change again the data type. Alright. So this is, see, the program has now become very simple. If you want to change the type of another data type or variable of another data type, then you have to just copy the same code and just change the data type. So it is very. So what I will do is I will write this code again, but this time the temp is holding the unsigned long integer data type. So it is actually holding the 8 bytes or 64 bits of data. Let's run the program. Okay, it is giving some error. So we have to specify some other variable here. Temp1. Now let's compile. So it compiled successfully. Okay, we need to insert one more line, new statement here, say /n. Now you can see this is another variable which is of 32 64 bits wide. And now in the next line it is Indianness change result. You can see this data is shifted. The 78 has come here and 12 has come here. So this is how your program is working. So alright, so now we saw how to change the Indianness of program using the union, and we saw how to use the most important feature of union, that is the shared memory location. I hope now you have understood the concept of this union. So let's go back and see some of the important points related to the union. Though union is related to classes, there are many limitations related with the unions in C++. First thing, union cannot inherit any other classes of any type. So this is a concept of inheritance. In case of classes, when you create the another class which is actually derived from the base class, it can inherit all the properties of that class. But in case of union, it is not possible. So if you create a derived union class from the base union, then the derived union will not hold, or it will not inherit all the properties of that base union. Then union cannot be base class, as we just saw. Union cannot have virtual member function. We'll talk about the virtual member functions in the upcoming videos, but for now, understand you cannot specify the virtual member functions within the union. Then the no static variables can be member of union. Reference member cannot be used with the unions. Then the union cannot have member any object that overloads the equal to operator. And no object can be member of union if the object has an explicit constructor or destructor function. We'll talk all these points in the upcoming videos, but for now, just understand what are the limitations of unions when compared to the classes. The unions can be used similar to classes, they have a lot of limitations. So it is better to use the unions in C++, the way we use in the C programming, and let the other part be handled by in terms of the classes and objects. Well, it's up to you. Finally, we'll talk about the anonymous unions in the C++. What is the anonymous unions? Anonymous unions does not include a type name. The object of the union can be declared. So let's understand with the example. First, I will create one anonymous union here. So how to create? We have to just specify the type union, and you have to just specify the keyword union, and then these two curly brackets and semicolon. Inside this, you can specify the data member. Now here, anonymous union doesn't require the any union name. So specifying the union name is not required. And without the variable name or creating the variable of union, we can access this variables or the data members of a union, anonymous union. So we can just write the statement and then we can output like this. So this is how the anonymous unions work. You don't have to create a union name, you don't have to create a union variable. Without them, you can directly access this union variables or data members of the union. Well, this now union is local to this function. It is present in this main function, so it is local to this main function. If you want to specify union outside the main function, that is into a global scope, then the compiler will not work. It will throw an error. Why? Because if you want to specify the unions in a global scope, you have to specify the static keyword. Now the compiler has resolved this error. So you have to remember, you have to specify the static keyword when you create union in the global scope. The second point, anonymous unions tell the compiler that its member variables are to share the same location. So as we talked in this video earlier, all the members in the unions share the same location. So the same concept is valid for the anonymous unions as well. And however, the variables are referred directly without the normal dot operator syntax that we saw just now. Third point, all restrictions involving unions apply to anonymous unions. So whatever the limitations we saw earlier here, same limitations apply to anonymous unions as well. The only elements contained within an anonymous unions must be a data. No member functions are allowed. This is a very important point. You cannot specify or define the member functions within the unions, anonymous unions. They cannot contain the private or protected elements. This is also a very important point. You cannot specify any access specifiers within the anonymous union. And this we saw, global anonymous unions must specify it as static. All that. So these are all the important points related with the anonymous unions. Just want to tell one last point here. What is the size of this union, data members of this union? So As we saw just now, this is a 64 bits of data, and this is also holding the 64 characters. So this is also a 64 bits of data. So myte size in this case is a 64-bit data. What if you specify only a 32 bits of a data here? And what would be the size of union? Remember, the size will also be a 64 bits in this case, because the size of unions is also governed by the size of a variable, which is of max size or the max data size. In this case, data 1 is of a size 64 bits and data 2 is size of a size 32 bits. The size will be considered as the size of this data 1 variable, since it has the max number of bytes. The size is greater. All right. So this is all about the unions. I hope you have understood all the concepts we talked about the unions. There are many other points related to the unions that we have not talked in this video, and that we have discussed about the structures in the previous video. And those are like passing the unions to a function, returning the unions from a function, using the pointers, union pointers in a function, passing the pointers to a function in the unions, and returning the pointers from that function. So you can refer the previous lecture of structure to understand this different functionality related with the unions, and they will work similar to a structure. So thanks for watching this video and stay tuned for the next video.